All right, so a couple quick reminders. We talked about them in detail yesterday, so I'll briefly mention them today. Probably for the last time today, reminding you, or last time forever maybe, that I'll remind you about the email. If you aren't taking the test on May 5th, you do need to email Miss Davis. Make sure you let her know that you're not taking it on May 5th, so she plans accordingly. Otherwise, you'll likely be charged for it, regardless of whether you take it that day. All the calendars are on Axis. So there's the normal assignments calendar, and all the assignments are posted. There's also the extra calendar I put on the bulletin board page that shows you when we're reviewing and when we're taking the exam in class and so forth. I posted here at the bottom all 3 of our positive physics assignments coming up. 2 of them are homework, Unit 14 on momentum, Unit 17 on simple harmonic motion. And you do the work section. You can correct it as you go. If you do, you should get 100%. And those are both homework grades, last 2 homework assignments of the year. And then Unit 23 is a test. And all of them are open. All of them you can start anytime. They're all due after the break, in that order, 14, then 17, then 23, the 3 periods after we come back. So it is a test grade, that 3rd one. So it'll work just like the quizzes. You'll have to do it in the assessment, and then you'll finalize it and then go back and do the corrections, and you'll get the average between the original score and the correction score. And the tests are the largest portion percentage-wise of your grade. So this should be a great boost if you do it and do well. But if you don't do it or don't do it well, then it could be a big hindrance. So just keep that in mind, that when you look at the classroom management plan, the test category is the largest category. So make sure you're doing well on that. Any questions about schedule, anything like that? All right, so I think I showed you this question last time, but we didn't have any chance to work on it or really give you much time to start it. All right. Am I correct? Did we talk about the question? But
I think we started talking about it.
Started talking about it. Yeah, what I remembered is I just kind of read it and said, go for it. But
We all tried.
yeah, and so I don't even know how, I don't think I even gave you much time to work on it. So I want to give you a little bit of time today. So just a reminder about what the question says. We've got this uniform board leaning against a small smooth vertical wall. The smoothness makes it frictionless. The board is at an angle, theta, above the horizontal ground. The coefficient of static friction between the ground and the lower end of the board is 0.65. Find the smallest value for the angle, theta, such that the lower end of the board does not slide along the ground. So there is friction between the board and the ground, but there's no friction between the board and the wall. And my recommendations, as always, draw a picture, analyze the forces, choose a pivot point, and then resolve the torque. And there are other ways you can solve this without torque, but I haven't found one that is easier. I had several students last period try to see if they could come up with that, and none of them were able to successfully do it. I'm not saying that to challenge anybody, or I think solving it purely based on forces is pretty tricky. Not impossible, but pretty tricky. If you use the whole force torque combination, it makes it quite a bit easier. If you're looking for this worksheet, it's actually back there because it's the oldest ones. Those are all new ones. Well, those are old, but they're not as old. This is really old. This is from 2 units ago. It is on worksheet 2. It's question number 3. It's right after the truck problem. So if you have that worksheet where we did the truck, we've done 3 or 4 questions on that worksheet now. So I'll give you 5 or 6 minutes, see if you can make some progress, and then we'll start heading through the notes. Oh.
Okay, sweet. That's a tricky one. I use where it's about. 5%.
Interesting to see if you think that the other position is easier or harder than the way you did it.
I thought that the center was my only one to the center, but when I worked through it, I realized that they're all pretty much the same.
I chose where it hits the ground because you eliminate two forces in your torque analysis.
Yeah.
But I didn't even try it the other ways. I just seemed the first thing that came to mind when I was solving. Give you another minute and then we'll go over it. All right, so I saw Ethan just finished up one way. Did anybody else in here have enough time to finish it? How about anybody in the Zoom? Did any of you guys have time to finish it? Do you have an answer yet? No. How many of you feel a little bit stuck? Okay, fair number. Okay, so I'm going to show you what I consider the most direct way to solve it. Like I said, I've never actually tried it because I think it would be very complicated to solve it purely with forces. I think you could, but I believe it would be quite complicated, and it's complicated enough the way that I would do it with torque and force. So let me show you how I set it up. So there's a lot going on here, so I'm going to try to slowly show you piece by piece. So for right now, focus on the picture over here on the left. So I've got, so I'm talking about this area over here. I've got my wall. This black thing here is my board leaning against the wall. And there's my angle that it makes with the floor, theta, like it described. And then I just started drawing the forces. So I knew the ground had a normal force, but instead of calling it normal force, I just called it FG because the wall also has a normal force. So I just called it force of the ground and force of the wall, but they are both normal forces. So the ground is pushing perpendicular up with a normal force, and the wall is pushing perpendicular sideways with a normal force. So there's the normal force of the ground, there's the normal force of the wall. There's the friction force, and if the board slid, the bottom would slide to the left as you're looking at it to its right, I guess, depending on your orientation, but it would slide away from the wall. So the friction must be oriented towards the wall. So I put that on there, and then the board has weight. And so I just, instead of calling it FG, since I already used capital G for ground, I didn't want to have a capital and a lowercase. So I just put the weight of the board is just FB for board. So I got FG, normal force of the ground, FW, normal force of the wall, FF, force of friction, FB, weight of the board. Now, what I recognized once I drew the forces on there, there are only two vertical forces, the normal force of the ground and the weight of the board. And one's perfectly upright and one's perfectly downward. So the board should not fly up into the air or burrow itself into the ground. So those two vertical forces should be balanced. So over here, just beside the picture, I have FG equals FB, and I put vert underneath it. That's the two vertical forces should be equal. Horizontally, there's also only two forces. The friction is oriented towards the wall, but the normal force is away from the wall. So they should also be equal, because the board shouldn't fly away from the wall, nor should it dig into the wall. It says we're trying to find the angle where it just sits there. So everything has to be balanced. So I put that the weight force, or sorry, the wall's force has to equal the friction force. I'm going to change the color here real quick. Just, I think it might help a bit for one thing. So I'm going to change this color. Just, I don't know if it makes a difference, but for those that are more into those patterns, it might. All right, so same thing, just different color. That way you can see the red, and the red matches, like that's where I started. Maybe I should make that purple instead of blue, but so the red and the red matches. But I know that the friction force, because the equation for friction force is coefficient times normal. And the normal force is this ground's normal force, is FG. So I could calculate that friction force by taking the coefficient of friction times FG. So all three of those would have to be equivalent. So that's my force analysis, the picture, the forces, making my force equations. Then I went to torque, and I was remembering that torque is F times R times sine of theta. So I'm using that to relate the two torques that are going to be existing. I chose my pivot point to be here where the board meets the ground, because that means these two forces don't create torque because they're at the pivot point. And any forces that are at the axis of rotation can't create torque because the R value is 0. So the FG and the FF don't create torque. That means there's only two forces that do. So it just kind of simplifies my torque expression or torque equation. Now I know that only the FB, the weight of the board, and FW, the wall's normal force, would create torque. So the torque created by the board itself has to equal the torque created by the wall. Questions so far before we start breaking down the torque equation more? Any question about the forces or why those two forces create torque and the others don't in my design? Anything from the Zoom crew? All right. So over here on the right, I've got a new triangle I drew just to help you see where this whole 90 minus theta came from. This triangle is basically, if I started at my axis of rotation and went up to the force of the board and then down, I'm just redrawing that little triangle. So if this is my force of the board right here, then, and this is the theta that they described, this would have to be 90 minus theta because they're complementary. It's a right triangle and they're complementary angles. So they have to add up to 90. So when I think about the torque of the board, it's this far from the axis of rotation, half the length of the board, so it should be from the middle. And it's at some angle, which is actually 90 minus the angle they told me, the theta. So I know it's got weight. It's weight would be half the length of the board or expressed in the middle, so half the length of the board. And the angle that it makes with the board would be 90 minus theta. For the torque that the wall creates, there's some force that the wall is creating, that normal force, and it's at the end of the board, so that's the entire length, not half the length, but the entire length of the board. And the angle that it creates is the theta, because if we look here, we've got the Z shapes, we've got alternate interior angles. So we're doing a lot of geometry here in this problem. But those two are equal. So any questions on how I set up that torque relationship? Yeah.
It was just interesting because the way you did it, if you multiplied the whole thing by 2, you'd have 2 FWL sine theta. And my equation, since I used the middle, instead of FB, I just had FG on that side. And then instead of 2 FWL sine theta, I had FWL sine theta plus the same thing. So it's literally the same equation, just with different variables, which is interesting.
Yeah. Yeah, so in case you're not sure what he's referring to, he chose the middle of the board as his pivot point. So then he has 3 forces creating torque. So his initial torque equation looks different because he's got 3 different torque values. But then once you combine them, you end up getting to the same place. All right, so what I can hopefully notice now is, hey, there's an L on both sides. So those L's should cancel. There's an L on the left side of the equal sign. There's an L on the right side of the equal sign. So if I divide both sides by L, the L's go away. So that's the first thing I did. And I could have written 1/2 FB. I just wrote it as FB over 2 because while the L's cancel, the 2 doesn't. And that's all I did, just cancel the L's in that step. And then I made a couple changes in this next step. Back to geometry, I know that the sine of one angle equals the cosine of the complement, or the cosine of one angle equals the sine of the complement, right? They go that's how they fit in geometry. So I changed it from sine of 90 minus theta to just cosine of theta because they're complementary. And then I changed from FB to FG because they're equal according to my force analysis. And then I changed from FW to mu FG because FW equals the friction force, which is mu FG. So now I've gotten rid of my FB and turned it into FG. I've gotten rid of my FW and turned it into FG. And the reason I knew to do that is because if I look up here, I can see I've got an FG and I've got an FG in both the vertical and the horizontal. So if I can capitalize on the fact that I can relate the vertical and the horizontal through the same variable, I know I'm probably going to be able to cancel things out better. So just noticing that both horizontal and vertical have an FG value somewhere that's equivalent, I just sought for a way that I could substitute those into the equation. Any questions about that step? All right, the next thing I did is just put all the geometry on one side and all the algebra on the other side, so to speak. So I divided both sides by cosine to get those all over on the right, and I divided both sides by the mu FG to get all the just other variables on the left, and sine of an angle divided by the cosine of that same angle is tangent. Yeah, so it's just yet another geometry bit here. Sine over cosine is tangent. And you can see the FGs both cancel. So by substituting in so that I had FG in both aspects, I knew that I could get them to cancel eventually, which they do. And then in my last step, it's just a trig step. Solve for theta. So I take the inverse tangent times 1 over 2 times the coefficient of friction. And should get, I didn't get 37, I just remembered it wrong. 37.6.
Yeah.
It's like either I wrote it down wrong or I'm remembering it wrong.
Yeah. The calculator input was the same.
Yeah, I looked at you, that's exactly what I typed. Yeah. So pretty tricky question. You have to remember a fair bit of geometry. You have to recognize how you can substitute some things in it so you can get units, or sorry, variables to cancel. Any questions? So my initial thought was that I would now have you do another question with torque, so we'd get 2 this week. Since we kind of ran out of time Monday to get this one done. I was wanting to do this one and another one today. But I also want to make sure that we get through momentum. We might not get to center of mass, but I want to make sure we at least get through momentum today. So I think I'll put that off. If we have time at the end of the period, might do the same thing, show it to you today and talk about it later. If we don't have time, we'll just do it after break sometime for more review. But I do want to keep practicing torque problems, especially these with angles, because as you can see, the other torque problems weren't simple, but when we start throwing in angles, it raises the bar another level. And so I would like to do at least one more with angles together as a class at some point. But we may or may not have time today. So let me go ahead and cover this back up and we'll move on. All right. So let's get into some further discussion of momentum. All right, so let me hide this so you can see the titles. So we're going to talk about today what happens if the collisions aren't all on one plane. So when we did the examples Monday, they were all just going horizontal and colliding with each other. But what if they don't go horizontal? What if they're going at other angles? So I've taken the simplest scenario I can think of that has 2 objects that aren't just moving in a single plane, just both horizontally or both vertically, but they're moving different. And I want to show you how we can work through using momentum this kind of a problem. So the scenario says we've got a 3 kilogram object moving 4 meters per second horizontally. We've got a 2 kilogram object moving 5 meters per second vertically. They're going to collide and stick together. And the question says, or instructs us to find the speed and direction of these 2 objects after they stick together. So here's what's visually happening. Hopefully, there we go. They stick together and they're going to go off in a given direction.
So we're doing 2 dimensions now.
All right, so we're assuming there's no friction or air resistance or anything. It's just purely the momentum is conserved. So there's no external forces that we need to consider. And if all we needed to know is what direction and what velocity they were moving right after the collision, that would be enough. I mean, if there was friction, eventually friction would bring them to a halt. But if we just want to know their initial angle and their initial momentum or velocity, we could ignore that as an external force anyway. So I would encourage you as we work through this one. Yesterday when we were, or Monday when we were going through those other examples, I said, hey, you probably don't need to write these down. It's going to be kind of the same thing over and over. But this one problem today, I do suggest that you write it down because we're only going to do one of them. And it shows kind of a pattern that may or may not be that intuitive for you. And so if you have it in your notes to go back and look at, I think it could be handy. So up to you. Obviously, I don't collect and grade your notes or anything, but this is one problem where I would suggest you may want to jot some things down. So, well, how do we figure this out? So going back to our setup, let's look at the green one first. And I think the best way to resolve this kind of a collision is to break the movement of each object down into its X and Y components. All right, so the X component for this one would be for momentum. We're looking at a momentum analysis here. Remember, momentum is mass times velocity. So if I'm just looking at the X value, it's got a mass of 3 and an X velocity of 4. So it has a horizontal or X component of 12 kilogram meters per second in terms of its momentum. What's its Y component? 0. Yeah, it still has a mass of 3, but it's got no velocity vertically. So it doesn't have any y component. Now, I chose this one because it's fairly simple and I wanted to start at least at a lower level of this kind of a problem. But let's say that instead of perfectly sideways and perfectly vertical, what if they were coming at angles? Well, I wouldn't change my approach. It's just that I wouldn't have 12 and 0. I'd have, you know, two different numbers, and neither one of them would be 0 anymore. All right, so the strategy would be the same whether they're going at 90 degrees to each other or not. It's a simpler strategy, or it's a simpler result here because the y value is 0, so it just kind of cancels out. If we look at the orange object, it's got a 2 kilogram mass moving 5 meters per second. So its horizontal component of momentum is 0 because while it has mass, it has no horizontal velocity. So the x component of its momentum is 0. But what's the y component of its momentum?
5 meters per second.
Times
2 kilograms.
Okay. So it's going to have a momentum vertically of 10 kilogram meters per second. Now, at this point, I want to make sure you're not missing something that may not be obvious, again, because the green one is only going horizontal and the orange one's only going vertical. When I start putting these vectors tip to tail here, in this case, the blue one is only from the orange object and the green is only from the green object. But if they were both going at angles, this wouldn't be 0 and this wouldn't be 0. So to get this value, I would have to add this x number with this x number. And that's really what I'm doing here. It's just that 12 plus 0 gives me 12. But if this wasn't 0, I wouldn't just use this number. I would add them together because I would need the total x momentum of the two objects combined. All right. Same thing for the vertical. Where this 10 is not just the orange one, it's actually the orange one plus the green one. It just so happens that the green one doesn't have any. So we're saying it's 10 plus 0 to get this 10. But again, if they were going at angles, this would be 10, but this would not be 0. So we would, or I guess it wouldn't be 10 either if it's going at an angle, but we would have to add the two together. Okay, so when we start putting our triangle together of momentum, we add the x's, we add the y's, and the power of breaking it down into x and y components is if these aren't moving perpendicular to one another, if they are moving at angles, once I separate this x component and this x component, and I separate that y component and that y component, the components are perpendicular to each other. So I am creating a right triangle, even though they didn't collide at a right angle in that alternate scenario. Does that make sense? So the strategy would be exactly the same. You just wouldn't have 0 here or 0 there, and you'd be adding them together to create your resultant triangle. So now I know when they collide, their resultant horizontal velocity will be 12. Their resultant vertical velocity will be 10. So what's their overall resultant? How do I find their overall resultant momentum? I think I said velocity, but I mean momentum. How would I find their overall resultant momentum? Yeah, easiest way would just be to find the solution through Pythagorean theorem. And I'm just going to recognize that, hey, if they have this much vertical and they have this much horizontal, the result is going to be this, the third side of the triangle. And I can use Pythagorean theorem to find that value. What can I use to find the angle? Yeah, just use trig, right? So nothing new. Like I can find the side, the third side by Pythagorean theorem. I can find the angle by trig. So there's really nothing new in this problem. It's just a matter of starting to recognize, hey, when I've got two things not moving just perfectly parallel to one another, I need to break it down into x and y. And I need to add the x's together, I need to add the y's together, create a resultant triangle. Then I can find their resultant momentum and their resultant angle. So in the end, we can prove here that this angle would be 50.2 degrees from vertical. And you could use 39.8 degrees from horizontal if you wanted to. It doesn't matter. You just have to specify what your angle reference point is. Is it from vertical or is it from horizontal? And then the value of that momentum is 15.62 kilogram meters per second. Now they haven't used sig figs, but they're not actually done yet. Because the question didn't say what's the resulting momentum. The question said what's the resulting velocity. But to find the resulting velocity, we need to figure out what the resulting momentum is. Okay, so we have to go through this step to get there. So any questions so far on how we can create this combination triangle to determine the resulting momentum of these two objects after they have collided and stuck together? Make sense so far? All right, so then how do I find the velocity? Well, in terms of the direction of the velocity, we learned yesterday that the direction of the velocity has to be the same as the direction of the momentum. So when they collide, they have momentum along that line, and their velocity would also be along that same line, right? Because momentum is mass times velocity. They're both vectors. So if my momentum is in that direction at 50.2 degrees from vertical, my velocity has to be in that angle 50.2 degrees from vertical. And now I know the resulting momentum of the entire system. What is the equation for momentum? P equals mv. I know the value for P, 15.62. Do I know the value for M?
Yes, sir.
3 plus 2, right? They're stuck together, so 5 kilograms. So now I can just use that resulting information with the straightforward momentum equation. I know the momentum, I know the mass, so I can find the volume, or not volume, velocity of 3.12 meters per second. And now they have actually used sig figs because they're at their final answer. So if you have two items colliding that are not both moving in the same plane, break it down into x and y components, add all the x's together, add all the y's together, and create a triangle. Find the resultant of that triangle, find the angle of that triangle, or one of the angles in that triangle, so you can give a direction. And recognize that the direction will be the same as the velocity. And once you know that resultant, and you know the mass of the items, you can find its final velocity. So it's a multi-step kind of a problem, but the strategy is consistent with a lot of other kind of problems you would use. The same sequence of steps. Any questions before I move on? All right, so for the next one, it's going to be a question where, in true College Board style, hey, solve this math problem, but we're not going to give you any numbers.
Yay.
Yay, that's favorite. All right, so here's the math problem. With no numbers. Oh, by the way, I mentioned this term last time, and we're going to come back to it again today. But when objects collide and stick together, we call that an inelastic collision. An inelastic collision. In this example, we've got a tennis ball bouncing off the wall. And in this scenario, we're going to say that this is more of like an elastic collision. They're not going to stick together. The ball's not going to stick to the wall. Now, we'll learn that there's sort of a middle gray area between those two extremes. And the middle gray area is actually more abundant than either extreme. But we'll learn that a little bit later today. So for now, I just want you to get the basic idea that inelastic, just at a very simplest level, they stick together. Elastic, they bounce. Okay, but the gray area in between is what we'll hammer home in a few minutes. So here we've got a tennis ball arriving and leaving a wall with the same speed and the same angle. That's the law of reflection, actually, which we don't learn anymore because they took waves away. But as it comes in and bounces off the wall, it comes in at a certain angle, it leaves the same angle. There's no inelasticity, there's no stickiness, it doesn't stick to the wall at all. And the question they want us to determine or answer here is, what is the ball's change in momentum? And what is the wall's change in momentum? And it may seem weird, the ball is clearly changing momentum. It's going one way and then it goes a different way. So it definitely has a change in momentum. The wall may say, well, wait a minute, how can the wall have a change in momentum? But if I push on this wall, I can actually feel it give a little bit. Like, not a lot, but I don't have to push very hard and I can kind of feel it give a little bit. So if it moves, there's an acceleration. There's an acceleration, there's change in velocity, right? Even if it's just a very small bit. So this wall doesn't have to like move from point A to point B. It just has to move even in the least bit to have a change in momentum. Now, the change in momentum, remember, is mass times velocity. So this wall has a huge mass, its velocity change is gonna be very, very minuscule, right? Probably unnoticeable. The ball has a very small mass, it's gonna have a large change in velocity comparatively. But they'll both have the same change in momentum. So how do we break this down? They haven't given us any numbers. Well, we have an angled movement here, so what should we do to determine our momentum based on what we just practiced?
Break it into parts.
Yeah, break it into parts. So let's look at the incoming scenario first before it hits the wall. It's coming in with this kind of momentum, right? That's its approach to the wall. And that momentum will have an X and a Y component. Make sense? Now the X component, because it's adjacent to the angle, would be mv cosine theta. The hypotenuse is mv. The adjacent we would find using cosine of theta. And they put a negative on it because they're using the normal, hey, anything to the left is negative, anything to the right is positive, anything up is positive, anything down is negative. They're just using the standard directions for positive and negative. So since it has initially a horizontal component to the left, they've made it negative. And then the Y component would be the opposite of the triangle, so they use sine. So, and then because it's down, they also made that negative. So the Y component of its momentum would be negative mv sine theta. Questions about that breakdown?
It's just about like the negative terms, like where you're saying like left and down. So like,
Because at this point, the ball hasn't hit the wall yet. We're looking as it's approaching the wall. And so it has a leftward movement and a downward movement. And just like we normally did with forces and everything before, unless we say it's otherwise, we assume left is negative, right's positive, and down is negative and up is positive. So since it's left, they're saying it's negative. And then since it's down, they're saying it's negative. Now, when the ball comes back, it's moving to the right, so that's going to be positive.
oh, okay,
That makes sense?
but it's still going down though,
Right.
so it's fine.
So that's going to stay negative.
Oh, okay, yeah, I see.
See what you're saying?
Yeah.
Yeah, so if we look at after it hits the wall, it's still going down, so its Y component is the same thing, actually, it hasn't changed. It's still negative mv sine theta, because it's still the opposite side of the triangle, so sine. But it's still downward, so still negative. But the horizontal part, now it's not going to the left anymore, now it's going to the right, because it bounced off the wall, so now instead of negative mv cosine theta, now it's the positive. Tracking okay so far? Any questions at all? So if I want to find the change in velocity, what do I do? Not for this problem, just generically for any question. Change in velocity at its root meaning.
Like to subtract the final velocity from the initial velocity.
over time.
If I just want to find velocity, just final minus initial, right? Or if I want to find the change in time, final minus initial. Change in position, final minus initial, right? Like that's the standard. So if I want to find the change in momentum, final minus initial. We know the final, we know the initial, so let's just show some subtraction. Even though we don't have numbers, let's just do it with equations. So in the X direction, our final is positive mv cosine theta, and our initial is negative mv cosine theta. But when you subtract a negative, you're adding, so that becomes 2 mv cosine theta. So our change in horizontal momentum is 2 mv cosine theta, positive 2 mv cosine theta. If we follow the same premise for the Y, our final is negative mv sine theta. Our initial is also negative mv sine theta. Anytime you subtract something from itself, you get 0. There is no change in the vertical momentum. So for part A, determine the ball's change in momentum. Well, it's not changing vertically, it's only changing horizontally, so its change is plus 2 mv cosine theta. Only in the X direction. So because of the law of conservation of momentum, assuming there's no friction or sound or energy loss, or just assuming this bounces off and there's no energy loss, what would the change in momentum have to be for the wall? The same magnitude, but
Opposite direction.
opposite direction. So the wall's change in momentum would just be negative 2 mv cosine theta. They have to have the same value, just opposite direction. Yeah, Ethan?
For College Board, would it be acceptable to say 2 mv cosine theta to the right and then 2 mv cosine theta to the left? Or would you want the plus and minus in the x direction?
You could say it right and left. That'd be okay.
And then you would leave off the sign because it would get confusing.
Yeah, I wouldn't put like plus to the right and
Okay.
negative to the left. I would just say 2 mv cosine theta
To the
in the
right.
x direction to the right or something like that. Yeah, or to the right in the x. Yeah. So either use the plus minus scenario or right and left. Don't do both.
Yeah.
Because then the grader has to determine,
Whether
do
you-
they mean a double negative like or not, and then they probably can't give you full credit
That makes sense.
because then they're having to guess something about your reasoning. Any other questions about this example? All right. So let's go on to some other scenarios. So I've mentioned that when things stick together, we call it an inelastic collision. And then just on this last example with the tennis ball, I mentioned that that's more like an elastic collision. But here is a nice little table that summarizes actually 3 scenarios, because if it's elastic, it just is. But if it's inelastic, it can be completely inelastic when they actually do completely stick together, or it can be partially inelastic where maybe there's a little bit of stickiness, or maybe some sound is lost as wave energy, or maybe there's heat loss due to thermal energy. Yeah, Kate?
Kind of like those sticky slap hands you get for like party favors, those little cheap things that you.
They stick at the
Yeah.
wall, yeah. So that would be
Stick
an
to a
inelastic collision, they just stick. But like those 2 sad and happy ball things that you guys were playing with before class, you know, neither one of them was perfectly inelastic. One was not quite elastic, but it was pretty close. The other one was not quite inelastic, but pretty close. They both were actually in the middle, which is where most things exist. Most collisions are somewhere in the middle. You very rarely see something entirely stick together, although you can. This is more common than truly elastic. In fact, I would argue there is no such thing as a truly elastic collision unless it's only because of magnetic forces that cause it. So like if you have 2 protons coming together, they don't actually have to touch, right? Because of the magnetic forces, they would repel and bounce off without actually ever touching.
And there's no way to lose energy.
So there's no sound there, because there's no physical collision, there would be no loss of energy. So outside of that kind of a scenario, so in other words, with all the things we would normally deal with in life, we're just not going to see that. That's going to be, 99.9% of the scenarios won't really be elastic. On the other hand, they'll sometimes say 2 pool balls on a table, like billiard balls on a table, collide elastically. Well, that can't be true, because when they collide, you would hear something. So energy was lost. And if energy was lost, this isn't true. So that it's not truly elastic, but they're saying it is, so solve it that way. So sometimes they'll give you that. It's kind of like saying neglect air resistance, neglect friction. They're just saying, hey, it's elastic, even though in reality we know technically it's not.
But it's really
It's really close, yeah.
Well,
Andy?
so like those sticky hands, like I'm thinking about this right now. And
Kate
like-
got you on that.
yeah, he's like, let's say you hit a paper. I don't really think it makes that much of a sound. Like if it does, it's like almost nothing, unless you like really like swing it, but like, wouldn't that be kind of close
To this.
Yeah.
Yeah, but what we're gonna see on the next slide is a little more detailed than this one. So let me dig into this just a bit more. So there's very few kinds of elastic collisions. Sometimes it's close enough, they'll say it is. And just if they say it is, go for it. Just assume it is. And that means momentum is conserved and kinetic energy is conserved. that is a very easy problem to solve because now you can approach it from momentum or energy. You can do both even, and then you can create a system of equations. If it's perfectly inelastic, that's typically pretty easy to solve because then they're always going to have the same velocity at the end because they're stuck together. Like when two trains hitch together, or when a tackle, like a defensive back tackles a running back or something like that, you know, that they stick together, and so they're going to end up with the same velocity. And so those are a bit easier to solve. It's these middle ones that are harder to solve because in these middle ones, they don't stick together, so they don't have the same velocity afterwards. They have different velocities, but some energy gets lost, so you can't use this. So you're stuck kind of with momentum only and potentially two variables that you don't know. All right, so if that happens, then there's going to be some other clue in the question. So maybe they tell you how much work was done, and then you can convert that to the energy loss, something like that. Or maybe they'll tell you the velocity of one of them afterwards. So then you can find the velocity of the other. So there would have to be some other thing given that we haven't seen yet in any of our examples. So just kind of trying to prepare your mind for how this can show up in different problems. So I would say, you know, there's really very few elastic collisions that exist. There's a fairly good number of perfectly inelastic collisions when they actually stick together, but there's far more partially inelastic where, and it doesn't mean that when we say inelastic, I kind of simplified it earlier saying, yeah, they stick together, it's inelastic. That's just if it's perfectly inelastic. What inelastic really means is there's energy loss. So if it's perfectly inelastic, there's energy loss, but because they stick together, it makes the problem easier to solve. If it's partially inelastic, there's energy loss and they don't stick together. So you got two ending velocities. All right, so hopefully that makes sense. Here's just another slide to see the same information, but in a little bit more complicated way. I don't know that it's necessarily that valuable, but it was from your book, so I'll show it to you. I took the other image from a different source that I like a little better, but this is how your book summarized it. You can see in this column, it's just a lot of information, but it just says the same thing over and over again. All momentum is conserved during this collision, just keeps repeating that. And then the before momentum equals the after, just keeps repeating that. So there's a lot of stuff there, but it's not a lot of information. And then for the kinetic energy, no kinetic energy is lost, and then kinetic energy is lost, and then kinetic energy is lost. And so before and after is equal because it's not lost, but here it's not equal because you got some gravitational, or not gravitational, dissipated energy lost from the object. So, and it's also strange to me when they call it gained. That I think depends on how you define the system, whether you would consider it gained or lost.
It gains negative energy.
Yeah. So depending on how you define the system, that makes sense in some scenarios, but a lot of books do talk about this, and that's why your book follows along and uses that internal energy scenario. So this table is true as long as there's no external forces. But remember, when we're looking at energy, when we're looking at work, when we're looking at collisions and momentum, we define the system. We decide what goes in that circle on our system flow. So if we don't want there to be any external forces, everything that has a force involved, throw it in the circle and include it. And then you define the system in such a way that this works. So you just have to look at the problem and say, hey, oh, they said neglect air resistance. Okay, air's not in the circle and that's not an external force. Neglect friction. Oh, the table's not in the circle and I don't need to worry about that force. There's no external friction force. So if it isn't neglected, put it in the circle and account for it. And then you can still use these principles. All right, so let's look at some examples of movement here. Slide this group back over here. We're going to look at 3 examples. And again, here is where I would say I don't really necessarily need to write all this down. We're going to look at partially inelastic, completely inelastic, and elastic and kind of see the difference. In every case, we're going to have a 2 kilogram moving at 5 meters per second and a 3 kilogram moving at 2 meters per second in opposite directions. But in this case, it's partially inelastic. So as they hit, these two are going to collide in an inelastic fashion, but not so inelastic that they stick together. All right, so we know that there's going to be some energy loss. So they do bounce off of each other. And now in this case, there's nothing really to solve here. They're just wanting to kind of prove to you what that chart shows us. So afterwards, the orange one now is only going 0.5 meter per second, whereas it was going 5 meters per second before. And the other one was going 2 meters per second in the leftward direction. Now it's going 1 meter per second in the rightward direction. So if we do the momentum analysis, we know momentum is conserved. Just to make sure you didn't miss that, it's conserved in all types, right? Every kind has momentum conserved. All right, so we can do our momentum analysis and sort of prove, because we didn't have any missing pieces, we prove momentum is conserved. But because it's inelastic, energy is not, kinetic energy is not conserved. Now, the total mechanical energy should be, if depending on how we define the system, but the kinetic energy is not. We do have an equation for kinetic energy though. So if we do a kinetic energy analysis using our 1/2 mv squared, the kinetic energy of the orange ball before was 25 joules. The kinetic energy of the blue ball before was 6 joules. Afterwards, again, because there were no missing variables, they told us everything. Afterwards, the orange one only has 0.25 joules and the blue one only has 1.5 joules. So they went from having 31 joules of energy to now only having 1.75. So there was a loss of 29.3 joules. And they call it here, again, in your book, they instead of using dissipated or thermal, they use internal, because all of that energy had to come from the internal initially. All right, so the kinetic energy that was lost is internal to the system, 29.3 joules. All right, so they're just basically proving what the chart was telling you. All right, what if it's completely inelastic, where they do stick together? So the math on this one's going to be like what we saw yesterday. Here they don't tell you the velocity, but based on what we did last time, Monday, I guess, not yesterday, we should be able to find that pretty easily. We did that a bunch of times before. So we know that because it's a completely inelastic collision, there is going to be lost kinetic energy. But they stick together, so they have the same final velocity. So we know this one has a momentum of 10 before, this is -6. They are stuck together, so they got a total mass of 5, and they're moving at the same velocity because they're attached. So just like we did on Monday, we can calculate this velocity. It would be positive 0.8 meters per second. Now, if we do the kinetic energy system analysis, it's inelastic, so we know there has to be energy lost. Would you suspect there's more or less energy lost when they stick together?
Wait.
Guessing more? Yeah, and energy is going to be lost. There's a little bit extra loss when they stick together. So instead of 29.3, it's not much different, but it's 29.4. But the same principle. It still had 31 to begin with. Now instead of 1.75 at the end, it's 1.6. So it's a difference of 0.15 joules. A very small difference, but typically there's a little bit more loss when they stick together than when it's partially inelastic. But again, just proving that any kind of inelastic collision, you will have loss of kinetic energy. And finally, what if it's an elastic collision? So in this case, we've got our 2 kilogram object moving at 5 meters per second. We've got our 3 kilogram object moving at 2 meters per second again, same scenario, but this time they bounce off of each other. And we don't know the velocity for either.
2 and 5.
So because they have different masses, we could find some proportionalities and discover it, but let me show you how we can also integrate what we know about energy and momentum together. So if we think about the momentum, we know that beforehand they had 10 and 6 in the opposite direction. So a total of 4 momentum before the collision. Afterwards, we don't know it, but we know it will be 2 times whatever V3 is plus 3 times whatever V4 is. So we don't know what they are, but we do have an equation. Now, if all we knew was momentum, we would be kind of stuck, right? But we do know that because it's elastic, kinetic energy is conserved. Since kinetic energy is conserved, we can use the kinetic energy equation and know that there is no loss. So whatever it starts with, it has to end with the same amount. So if I use my 1/2 mv squared for the first object and the second object, and this first object after and the second object after, I get another equation where I still have that same 31 joules of energy before. And on the other side, I don't have an answer, but I've got same here, V3, V4. So now I've got two equations with the same variables. How do we solve a problem when there's two equations with the same variables?
Graph them.
Some kind of system solution, right?
Yeah.
Graph them, substitution, elimination, whatever we decide to do. So if you like graphing, get out your TI Inspire, graph these equations, find their point of intersection, right? And we're gonna have a couple of points, right?
Yeah. And then.
Elimination.
Yeah, if you go with elimination, then you're gonna have to square one of them or square root one of them, because the bottom one has V3 squared and V4 squared, but in the top one that's not squared. So if you're gonna use elimination, you're gonna either have to square root the bottom or square the top, but you can do, right? If you do substitution, that may be the simplest route, but that's what they do here. I don't know, you may prefer another method. I always liked elimination when I was a student, but substitution works pretty well for this one as well. You would have to do some manipulation to do the elimination part, since you have to square these. So you'd end up having to squaring them and then also multiply by something to get something to cancel. So substitution is probably a bit easier for this one. And so here are our two equations, the one we found from kinetic energy and the one we found from momentum. So if I solve this bottom one for V and think about the system of equations approach, just divide everything by 2, isolate the V3. So V3 from this second equation is equal to 2 minus 1.5 V4. So now I can substitute that back into the other equation, right? So we're back in algebra class. So when I substitute that in, I'm going to have that 2 minus 1.5 V4, but it's going to be squared, and then I'm going to have to combine like terms, and then I get this 0 equals 3.75 V4 squared minus 3 V4 minus 27. So now I'm going to have to go and use my quadratic equation.
This is the part where you use the solve function.
Yeah, so if you have your TI Inspire CAS, you're cranking out your solve function right now. You didn't get the CAS one?
That's unfortunate.
Yeah, that's sad. And whenever you get, and now here's the good news. You don't have to use quadratic formula on the AP exam. They give you ones that either work out where there's only one solution, like so there's no B term. Or they give you one that's easily factorable, so you don't have to use the quadratic equation.
Aren't you?
Generally
You
speaking,
just plug it back in,
what's that?
plug them both back in.
Yeah, but I was just saying, you're never gonna have to use the quadratic equation to find those two solutions. They'll either give you one where there's no B term, so it only has one solution, or they'll give you one that's easily factorable, so you don't have to use the quadratic equation.
Don't they like put your calculator in test mode so you can't use the solve function?
No,
Let's go.
test mode only.
Is that only for math?
No, they put it in test mode, but it just disables documents, so you can't smuggle notes in, and it wipes your scratch pad once you take it out.
That makes sense.
Yeah, it just makes it so there's no.
So it basically like factory resets it like temporarily.
Epic.
All right, so now that we know the two possibilities for V4, it's either moving 3.6 meters per second to the right, or it's moving negative 2 meters per second to the left, or 2 meters per second to the left. Now we can just plug both of those into our other equation and figure out what V3 would be. So if we use 3.6 to the right, then V3 is 3.4 to the left. And if it's 2 meters per second to the left, then it's 5 meters per second to the right for the other one. So we have two options. Sometimes, depending on the scenario, only one option makes sense. But again, they even put this, your textbook actually even put this in there. I got cut off, but it says quadratic equations are not used on the physics AP exam. So I just got cut off there.
Very cool of them.
Yeah. So you don't actually have to be able to use the quadratic equation.